So the most important thing, so not that you get confused, on the syllabus states that for for next week's topic, so the data screening and testing of assumptions for statistical tests, that there will be a separate chapter on Blackboard from a different textbook. So actually, I was hoping to find a PDF version of that chapter, but it was impossible. So it's really hard. And I tried to scan it with my phone, but so it has like really small print, and it was just a nightmare. So you don't have to do, so the long story short, so you don't have to do any readings for next week. So just forget about that. So we will cover everything in class, hopefully. And I think we will be able to cover it. So just so that you're not confused. Then another thing is, I mentioned that in my email, if you're submitting your assessments after each lecture, so the muddiest and the clearest points, is very helpful for me. And by the way, thank you for the submissions. So please make sure that you submit your names, so otherwise I don't know who to give credit to, right? And try to do it by the end of Friday. So Friday of the week of the lecture, so by 11:59. In order to get credit for your submissions. So that's another thing. And so I hope that actually so many of the points that you submitted last week will become a little bit clearer today, because we will directly pick up the topic where we ended last week. And so we will repeat some basic concepts. So I actually have to check here my list. Right. So that's an important one. So I read on the so in the suggestion box that not everyone is happy with a group work. So so one of you at least raised the concern that it's very difficult to coordinate the group work during the pandemic. So to use the online tools that are available. And I just wanted to get a general idea. So whether so many of you share this impression, and where the problems are, because so I was surprised, because I thought in a virtual environment it's even easier to find times and opportunities to work together as a group, because you can always schedule a Zoom meeting, right? So we can, I thought it's much easier than meeting in person, right? So where you have to find a time where you can all come to campus, or where you are on campus. So perhaps you could let me know whether that's something that many of you find difficult, and why. So, and maybe I just don't understand what the problems are. I just want to get a better idea of a better sense of what's going on. So who, maybe we put it the other way around. So who's okay with a group work? So who finds it doable? You can just basically indicate in the chat whether that's something that you find doable or not doable.
Yeah, I was gonna say it was a challenge at first, because we're not used to doing group work right now in grad school, I guess. But we, like, at least my group coordinated a time a little bit earlier, and like we have like our own little separate WhatsApp group chat, so that way like we coordinate like that. So I mean, I just wanted to spill those ideas out there, if that works. But yeah.
Okay, yeah, thank you. In general, so that's also the feedback that I got from from you earlier. So I think it's helpful if all of you so first work individually. So on these, so basically that you try to come up with your own solutions, and then so you schedule a group meeting where you go over the different questions and discuss your solutions, right? And then you resolve potential. Yeah, so where you have like conflict or different approaches or different opinions. And I really think, I hope you will appreciate it as well. I really think it's very beneficial for multiple reasons. So first, you have to justify your explanations, and if you're challenged by your peers, so you're forced to think deeper about it, and also to explain your point of view, which will help you to really process and internalize the topics. And so it's also, I mean, you can get some help or some insights from your peers. So I think it's really, really important. It's also collaboration, right? So it's team. It's basically the ability to work together in a group, to find a compromise, to come up with a common solution. So, and that these are all things that I think are really, really beneficial and will benefit you in your future career, no matter what you're going to do. So I mean, if you still feel it's super challenging, or there are specific problems that I simply don't see, then let me know. But my idea was, right, so you work on your homework assignments individually, and then you you schedule a group meeting on Zoom. You basically the same way you would meet on campus for group work, and then you go over your individual solutions, and hopefully in most cases it will be you all come up with more or less the same solution, right? And then in cases where it's a little trickier, so you might have to reach a consensus and discuss your different approaches. Okay, so but again, so let me know if there for whatever reason are difficulties that you're facing because of particular situation or particular circumstances that I simply that I'm not aware of. And so if it's if it's a big concern, then we might find a workaround. Okay, so right. I also wanted to point out that I have posted our first paper. I mentioned that earlier, so there will be a bunch of papers that deal in a critical way with the way that statistics are approached in contemporary neuroscience and psychology. And so the first paper is posted. It's quite long, but it's also really, really important. And it's a major criticism of how we use a p-value and rely on the basically null hypothesis significance testing in neuroscience, and why it is not a good approach, what the weaknesses are. And it's highly, highly recommended, not only so the papers in general, not only as a way to improve your grade, but that is really, these are really topics that all of you should be aware of. Not only if you're planning to stay in research, then it's even more important, but also if you're in a position where you have to understand statistics and that's, as we have learned in our first class, so that is almost everywhere. So no matter where, even if you're a journalist, you have to understand stats and have to be able to interpret it. So highly recommended, right? So I posted the first paper. I also posted the first questions that is supposed to help a little bit get started with the discussion. And in general, so the comments need to be posted within 2 weeks of the publication date. So I will add that to the syllabus. So that means so you have 2 weeks from now to make your contributions, and I will add more questions as we move on with our discussion. Okay, so these were just a few organizational aspects, and now let's get started with our actual topic today.
I have a question.
Yeah, sure, Kimberly.
I'm sorry, I have a question. So you posted something on Blackboard psychology data, and when I tried downloading it gives me an error on my computer saying that I have to open it with a specific app.
Yeah.
And I downloaded R, like I used R. So is that like data to be used with R, or what is that? Because it won't even open.
Yeah. It is a DAT file, so it's basically just a text file. You cannot open it with R. You have to import it to R, and we will learn. So in our next lab, we will learn how to do that. So that is a data that you're supposed to work with for your next assignment, right? So it's simple. It's a plain text file, so you should be able to open it with any text editor.
This one, that's
right. So whatever text editor you have on your machine, so you can. It's a plain text file. Right. Okay.
Okay. I'm gonna check that again. Okay.
So. Okay, So today we are going to talk about statistical inference, and all the nice stuff that we were talking about last week will be important and part of that. So, but before we get started with statistical inference, so let me recap a few aspects, a few topics that we talked about last week, because so I learned from your feedback that not everything was crystal clear. So there were like a few muddy points, and hopefully we will able to cover that. So just as a reminder, so what was probability? And we know that the concept of probability is associated with the observation of a random variable. And so with the potential outcomes, the possible outcomes of this random variable. And the probability of a particular outcome is a proportion of times that the outcome would occur in a very long, so in an infinite number of observations. So probability, as a reminder, is a theoretical concept. If we are talking about the actual occurrences, then we are talking about frequencies. So as a reminder, to distinguish between the frequency distribution and the probability distribution. So two different things, empirical, theoretical. So in the probability distribution just specifies the probabilities for the possible values of a variable. It's a theoretical model. And so we have our different outcomes, right? So that we can denote as a value, that is an arbitrary label, right? So that is the value of our variable y, our outcome y. And so these probabilities are non-negative and they sum to 1. Yeah, so the range of all possible outcomes, so the probabilities for all possible outcomes of a random phenomenon have to sum to 1. So how is probability determined? And again, so I wanted to highlight that so that can be personal belief. Yeah, so it doesn't have to be objective data. It can be personal belief. It can be a mix of personal belief and objective data. So we use that often as a priori probability in Bayesian statistics. It could be empirical frequency, that is very often the case, right? So we are observing how often a certain outcome occurs in real life, and we estimate probabilities based on that. And it could be determined, so based on classical probability, which is based on our knowledge of a certain situation, right? So that is how we derive, so this theoretical assumption that the probability of rolling a certain number when we're rolling a die is 1/6, although in reality that will never be really true. It's a theoretical assumption, right? There is no such thing as a perfect die, but so this is our model, right? Our model of rolling a die. And that model says, so the probability of getting, so each of the 6 outcomes is the same. So it's 1/6 for each possible outcome. So that is a classical probability concept. So, and then we were talking about a number of rules. So when it comes to that we need to know when we deal with probability, the first was a complement rule, and that is just the probability of an event or an outcome not occurring. And this is simply 1 minus a probability that it occurs. Well, it's called the complement rule. Then we were talking about the addition rule for disjoint events. Just a reminder, so disjoint events were mutually exclusive events. So that means events that cannot happen together. So if my 2 events were, a randomly selected person, so the hair color of a randomly selected person from the population, so in potential outcomes are blonde, black, brown, white, gray, whatever. So then a person cannot have blonde hair and brown hair, right? So these are mutually exclusive events. So disjoint events. And the addition rule, so for our disjoint events, as a probability that we have event A, so as an outcome, or event B, is just a sum of the individual probabilities. Then we were talking about the general addition rule, so that also includes the non-disjoint events, so the events that are not mutually exclusive and can happen together. And in this case, so of course, right, so there's a reminder here. So the Venn diagram is always very, very helpful when talking about probabilities. If we would add the probability for A and the probability for B and we have some overlap, then we would count, so this probability of both occurring together 2 times. So we have to subtract this probability, right? So the overlap here between the two. So the next important rule is a multiplication rule, and that is a probability for 2 events occurring together. And here we have to differentiate between independent events and dependent events. So again, so the easier case are the independent events. And here, so the probability that event A and B occur together is just a product of their individual probabilities. And then again, as a reminder, so 2 events are independent if the fact that event A occurred does not influence the probability that event B will occur. No? So that is, we had this example for picking, so 2 individuals randomly from the population, and then determining their hair. So let's say again their hair color. So then, so the outcome of my first observation, so a person has blonde hair, has absolutely no impact on the probability of the hair color for the next individual that I picked from my population, right? Could be blonde, brown, red, whatever. So the first outcome does not influence the probability of the next outcome. However, if I would, instead of randomly selecting 2 people from the population, if I would select a pair of siblings, then so basically the outcome of my first observation, so the hair color of the first sibling, would definitely have an influence on the probability of the second outcome, right? Because siblings are more likely to have the same hair color. So there's some inheritance. Okay, and that's why so we have the general multiplication rule for so that also includes the dependent events. And here, so we have to work with what we call the conditional probability. So let's A and B denote the hair colors. So what is the probability for, so for siblings, both having blonde hair, So, and that is just the probability of one sibling having blonde hair, and then the probability of the other sibling also having blonde hair, given that the first one had, so basically that we already know the first one has blonde hair, right? Or we could also say, so what is it? It doesn't have to be both blonde, right? It could be one blonde, one brown. But we simply have to take into account so that the second event, might be more or less likely depending on the outcome of the first. And that's why what we have to take into account is how likely is it, if we already know that the first one was blonde, how likely is it that the second one is blonde too? And that is basically what we have to put into that equation here. Okay. Then we were talking about probability distributions, very important concept. And the probability distribution function simply gives a probability of each possible outcome of a random phenomenon. So if we would, for example, determine what is the intelligence quotient, so the IQ for women in the United States, right, and would randomly select women from the entire population, then we would observe what is measure their IQ, right? And then we know it could be any value that is on our scale for potential outcomes of our test. And so then we can just determine what is the probability for each individual test score, right? For our entire population. That is our probability distribution function. So it basically assigns the possible outcomes of our random phenomenon, of our random variable probabilities, corresponding probabilities. And we have also talked about that it's important to differentiate between probability distributions for discrete variables. So we call this function the probability mass function, and for continuous variables. And for continuous variables, we refer to it as a probability density function. So here on this slide, that is again illustrated, right? So here we have the probability mass function for a discrete variable. We see on the x-axis, so these are the potential discrete outcomes. So it's a finite number countable number of outcomes, and each outcome is assigned a certain probability on the y-axis here. So that is our probability mass function. For a continuous variable, so there's an infinite number of potential outcomes, something like the height, for example, and the weight that can be measured on arbitrary to an arbitrary degree of precision, not necessarily measured, but the real height and the real weight is, right, as you all know, a real number. So the probability density function is a smooth curve in here. So the function assigns intervals of potential values, probabilities, right? So we basically so look at our range of potential values, and then so for a given interval, the area under the curve tells us what the probability is for a value to fall in that interval. And our y value on the y-axis is simply so the limit for letting that interval go to 0. And so I know that there was a little bit confusion of the relationship between the probability mass function and the probability density function and the cumulative, so that basically the cumulative counterparts. So the cumulative distribution function is simply, you could call it like a different display of the same phenomenon. So here we basically just, for the cumulative distribution function, so for discrete variables. So we just ask, so how likely is it to get a value that is the same size or smaller than this particular one on the x-axis. So let's say we have we have again our IQ, right? And they are discrete. So because usually we don't measure like we don't have an IQ of 97.5. So let's say we want to know what is the probability that the IQ that we measure is at least 90 or smaller, right? And so then we just sum up so the probabilities for, let's say that is here 90, right? So and we sum up the probability for everything that is under 90, right? So this probability and this, and we just put that here and the cumulative distribution function as a on the y-axis, right? So and that would be then, I mean, that of course is so that would be because that's about the 50th percentile, so that must be 100, right? So could be somewhere perhaps if that's could be in this case here this value, right? Because it's the most frequent category. If that would be our IQ of 100, right? So then so it would be about 50% of the population that has an IQ of 100 or smaller. Yeah. So and then we would keep accumulating, and then here that basically would be the highest possible value, which is for most intelligence tests, actually I don't know, 160 or something like that. So that is the end of the scale, right? And so and of course, so that would be 1 here because we cannot have a higher IQ. So there is no possible value higher than 100%, than 160. That's just, I don't know whether that's true. So so there might be differences between the different intelligence tests, right? So what the maximum value is. So and that would be the end of the distribution, right? The highest possible value, and that of course have to be 100%. I hope that makes sense. So the same idea applies to the continuous variable and to the probability density function. In the same way that we describe frequency distributions with statistics of their central tendency and their spread, we also use summary statistics for probability distributions that characterize the shape and their central moment, for example. And the most important ones are the mean, which we also call mu, right? And the standard deviation, which we also call sigma. So again, as a reminder, the Greek letters are usually used for the population parameters, whereas the Latin letters are used for our sample statistics. So the mean of a probability distribution of a discrete variable, I keep it to the discrete case because it's easier. So that it's just so the weighted average of the weighted average of all possible values. Yeah, the weighted average of all possible values. So each possible outcome is multiplied with a probability that this outcome will occur, and then we sum up across all possible outcomes. And then it's also called the expected value. And the expected value is a long-term average. Yeah? So don't think about it. So there was one question. So don't think about a single observation of a random phenomenon. We're always thinking of like an infinite number of observations. It's a long-term average. If you would, again, think of this IQ, so measuring the IQ of a randomly selected woman in the United States. So we do that over and over and over and over and over again, an infinite number of times. So what would be our long-term average for our observations, for our measurements? Right? In the same way, the standard deviation is a long-term average deviation of an observation from its mean. Same logic applies. Again, long-term, right? So observed over like an infinite number of observations of this random phenomenon. So a very important probability distribution is a normal distribution. So it plays an important role in statistics. And I just wanted to, you have heard about that multiple times. I just wanted to reiterate important characteristics of the normal distribution. So it is, of course, characterized by its mean and its standard deviation. It's symmetric. Yeah, so it has a bell-shaped symmetric curve. And the probability of a value lying between minus and plus standard deviations from the mean is about 68%, right? So 68% of all values are within one standard deviation from the mean. About 95% of all values are within 2 standard deviations from the mean, and almost 100% of all values are within 3 standard deviations from the mean. So yes, you can see here, so that's almost the entire distribution. And that is only true, so these specific numbers are only true for the normal distribution, right? So we know other probability distributions, like chi-squared and the F distribution, or the T distribution, right? It's also an important one, looks very similar to the normal distribution. But these specific, right? So these percentages of values within, so these standard deviations from the mean, that is only true for the normal distribution. So we were also talking about the sampling distribution. Sampling distribution is a probability distribution, right? But not of one observation, not of one value, but of a statistic that we calculate from our sample. For example, the sample mean, or it could be the sample standard deviation. So it's simply the probability that this statistic takes on the different possible values when we draw samples from our population an infinite number of times. And so a very important sampling distribution is the sampling distribution of the sample mean. So we use that because many hypotheses, right, are focused on the mean of the population, or the difference between means of different populations. So that's why this is a very important statistic and a very important sampling distribution. So in here again is this idea, right? So it's the figure here shows what the basic idea is. So we have a population. This population is characterized by a certain true mean. So there's a true population parameter and a true standard deviation. And then so we take repeatedly samples from this population. So for each sample, we determine the sample mean, so the statistic. And we basically, if we would do that in an infinite number of times, right? So these sample means would vary from one sample to the next, and we would get a probability distribution for these means. And that is our sampling distribution of the sample mean. And this sampling distribution again has a mean, an expected value, which happens to be the same as a population mean. And it has a standard deviation. Yeah, and this standard deviation also so can be calculated from the population standard deviation, and it happens to be so the standard deviation over the square root of the sample size. And that formula also implies that as the sample size increases, so as we basically we collect a larger number of subjects, observation units from our population, so the standard error decreases. It becomes more precise, right? Our estimate becomes more precise. The next concept we were talking about is a central limit theorem. A central limit theorem states that for large random samples, on a random variable, the sampling distribution of the sample mean is approximately a normal distribution. So it means if I just choose my sample large enough, then no matter what my population distribution is, so the sampling distribution of the mean will always be normal. Well, that's very desirable because it allows me to determine how close this estimated, the sample mean is to the actual population parameter. Because we know how the normal distribution is, so we know the probabilities, right? The percentiles for the normal distribution. And the good thing is that actually many sample statistics, so that the central limit theorem does not only apply to one sample statistic, not only to the mean, but also to others. Yeah? So that is what makes it so valuable for statistics. And again, so that was another question in the feedback that hopefully will become a little bit clearer today, but I want to address it right now. So the fact that we know that the sampling distribution of our sample mean is normal helps us to find the probabilities that for possible values of our sample mean. Because so we know that the sample mean falls almost definitely within 3 standard deviations from the population mean. So that means if we draw a sample from our population, so and we calculate the mean for the sample, then we know that so almost definitely that's the true mean of the population that this sample comes from is within 3 standard deviations from this value. That's what we can conclude because of the central limit theorem, because we know that the sample mean has a normal distribution. And that is true for basically this rule, right? So for a normally distributed variable, so almost all outcomes lie within 3 standard deviations from the mean. Yeah, that allows us to make that conclusion. Okay. So what I wanted to do now, and I didn't have time to do that last week, is I wanted to show you this fantastic application here. I hope you actually, can you see my screen? Yeah, okay, super. So you see the art of science learning from data. All right, fantastic web apps. So this is also referred to in the textbook. So this web page, and I can only highly recommend using it as often as possible. It's fantastic. So I wanted to just guide you through the different apps that it provides, and it will really help you to understand. It's like a little bit hands-on, right? Doing statistics by hand. So to explore the different tools that they provide. So here you can see for exploratory data analysis, so they have that for categorical, for quantitative data. So they have a random number generator here. And so they have, sorry. Okay. So we will use those applets when we talk about correlation, regression, right? So we will look at that, but right now,
Let me see your PowerPoint.
Oh, you don't see the, okay. Wait a second. Can you see it now?
Yes, thank you.
Oh, okay, super. So, and they also have applets for the sampling distribution. And so you see that's for sample proportion, for sample mean, for continuous population, and for the sample mean for a discrete population. So we will, right now, we will take a look at the sample mean for a continuous population. Yeah. And you see here you can select from different distributions, from different population distributions. So we just here some real population data, college debt, or they have college costs, college earnings, blah, blah, blah. So all sorts of things. And you can also pick from different population distribution types, like a uniform distribution, where each outcome is equally likely. A skewed distribution, right? So that is not symmetric, but has more outliers, more extreme values, either in the at the lower end or the upper end. So a bimodal distribution, or you can even build your own distribution. So let's first take a look at the real population data. Here you see all the values, right? So that is a college debt, so the median debt after graduation. And you can select the sample size, and then how many samples you want to draw from your, and here are a few things that you can adjust some visual features, right? So that they want to do the normal approximation, etc., etc. So let's start with a sample size of 5. Yeah. And then we use that data here. Let's say we wanna, let's just draw one sample, right? So for starters. And you can see here that it shows you the outcome for this one sample, right? So 5 values, so 5 students from the population, so former students from this population. Right, and here you, and the y-axis shows the frequencies for the particular outcome. So it's like 2 for the value, might we have n5, so we have 2 for something between maybe 24,000 or so. And so then we have 1 in this range here and another one, so around 35,000. Right, we see that our sample mean is 28,000 roughly, and this is standard deviation. So whereas our population mean is 23,708, and the population standard deviation is 5.9. So it's all right, and that shows us that is our sample mean, that is our population mean here. So we are not that far off, but quite, right? So let's draw another sample and see what happens. Right, so this is the frequency distribution for the most recent sample, right? So this time we have a sample mean of 27,729, and here's our new data point. Let's draw another one. So now per accident, right? We got really close to the actual population mean, right? So that is, let's draw another one. And another, right? We could do that. Let's just say we do that 100 times. Right, and then we get our here, that is our sampling distribution of the mean. So it's just the sample mean for all these 100 samples that I just drew, right? It's the most recent one here. And so, and you can see it looks pretty much already like a normal distribution, right? And we are getting pretty close to the actual population parameter. So the center of this sampling distribution, right? So it seems to align with the true population mean. So what happens if we now change the sample size to, let's say, 100? So what did just happen and why? What happened and why?
The frequency, I mean, the distribution looks very, very narrow.
It looks narrower, exactly. So what happened with the distribution? So what parameter has changed of this distribution, the sampling distribution?
Larger sample size and more samples. So because I see you put the sample size to be 100, but then you said how many samples and you put 100. So there's 100 different samples groups with 100 people in each one.
Yeah.
So that's a lot.
Yeah, I mean, so having 100 in a single sample versus only 5 changes something. It makes the sampling distribution narrower. So what changes here? What changes for the sampling distribution? What parameter changes of the sampling distribution? Does the mean change? No, the mean does not change. So what changes?
Would it be the deviation?
Exactly, the standard deviation, so also known as a standard error, right? Because it's a sampling distribution of the mean, right? So to differentiate that from the population standard deviation, we call it the standard error. Exactly, the standard error decreases. That is basically what what the formula tells us, right? So that's right. We have the square root of the sample size in our denominator. So it means a larger sample size, the smaller the entire value. Our estimate's becoming more precise, right? It's becoming more centered around the true population mean. Now, as compared to the small sample size here, where it's much wider. Okay, so and if you do that for 1,000, right? So we just see that, let's again do that. Right, so we basically just get a more. Hi, Arden. Mommy muss unterrichten.
There's only two.
Okay. Right, and if you do 10,000 and redraw that again, so you see, so the more samples we are drawing, so the more we have the typical bell shape. And at some point, it also shouldn't matter that much what our sample size. I mean, the sample size is always important, right? But so the bell shape, because we know from the center limit theorem, so that's the larger the sample size, so the more we have the so the more we approximate that it's a normal distribution, right? So if we choose that smaller, so and if we would do something, actually let me start over. So okay, let's say we have a skewed population distribution, yeah? So here, really skewed distribution. And then again, so we have a relatively small sample. Yeah? We are drawing a lot. I mean, it doesn't matter, right? So how many? And you can see that for a small sample, so we still see a little bit of a skew, right? So we still see this original skew from the population distribution or sampling distribution. However, if we make our sample size larger, this is gone. Yeah, so that looks very symmetric. That is very bell-shaped. So, and that is the idea of the central limit theorem. So if you just make, unfortunately, the simulation doesn't allow larger than 100, so sample size larger than 100. If you just make your sample large enough, so no matter how you're, right, so we can say it's uniform. And then we do the same thing here. So no matter, see bell shape. So no matter what your population distribution, so what's the distribution of your random variable, the population distribution as the sampling distribution of the mean will be normal if just the sample size is large enough. Okay, so very useful. I highly recommend using it as often as possible. Okay, so and now let's go to the topic of today's lecture. Let's move on. So how do we relate all these things to statistical inference, to statistical estimation, which is what we actually want to do. So we want to make inferences about population parameter, differences between population parameters, or all sorts of other relationships that we might be interested in population. So how do we use our sample data? How do we use sampling distributions to estimate population parameters? So for example, population mean. And so following the textbook, we will focus on two prototypical parameters, so which is a population mean for quantitative variable and population proportions for categorical variables. So we have examples for both. There are two fundamental ways how we're making estimates for our population parameter. And the first one, and the one that you are probably most familiar with, is called the point estimate. A point estimate just means that we are basically finding, or we're coming up with a single number for population parameter. Well, let's say we are interested in making an estimate for population mean, so then we come up with a single number that is our best guess for this population parameter value. So let's say we want to know what is the average height of men in Canada. We come up with a single number. That is our best guess or estimate for this parameter. However, so that is not necessarily the only way you can make an estimate for a population parameter. You could also give an interval estimate. You could say, all right, so I predict or I believe that the true mean of, so the height of men in Canada is between, I don't know, 5, 8, and 6, yeah, 6'1". Not a very precise estimate, but we could basically just give a range of values that we believe the true parameter falls in. And that is also called a confidence interval. We could have either give a single number, a point estimate, or we could give a range, which is an interval estimate. And as we shall see, the interval estimate is typically the preferred method of estimation, other than what you might think and what is commonly done. Okay, so let's talk about point estimators first. So somehow, in many cases, we want to know how good is our estimator. So we want to tell something about the goodness. So which in many cases also tells us how useful it is, right? So, and we have two important criteria that tell us something about the goodness of our point estimator. The first one is whether it's biased or unbiased. And the second one is whether it's efficient or inefficient. So what is meant by biased? And let's again focus on the mean, on the sample mean, because it's such a so easy to understand and ubiquitous statistic, and so the population mean such an important parameter. So what is an unbiased estimator of the population mean? An unbiased estimator is one that centers on the mean of the population distribution. So that means that if I want an unbiased estimator for my population mean, for the true parameter, then hopefully my statistic that I come up with has a sampling distribution with a mean that is the same as a population parameter. And that's what is called unbiased, right? So that means in the long run, I will be right with my estimation. I might be off for like individual samples, I might overestimate, I might underestimate, but on average, I'm right. And so similarly, not similarly, but so what I want from my estimator, of course, there's some variation, right? So it's different for each sample that I take from my population. But I want the standard error, so the variability of my estimator is to be as small as possible. And that is called an efficient estimator, if it has a smaller standard error, smaller variability than other estimators for the same parameter. So we already know that the sampling distribution of our sample mean is centered around the population mean. That means the sample mean is an unbiased estimate of our population mean. Again, in the long run, it is correct. For each individual sample that I take from a population, right, the sample mean might overestimate the true population parameter, it might underestimate the true population parameter, but in the long run, it will be correct. Yeah, so it underestimates as often as it overestimates. So there is no systematic bias in either direction. A biased estimator, say to the contrary, tends to systematically underestimate or overestimate the parameter. So on average, it's too small or too large. And a prototypical example for biased estimator is a sample range for the population range. So if I try to estimate the range of possible values, right, so the difference between minimum and the maximum in the population from a sample, so then I would systematically underestimate. So if I would use the range of my values in my sample, I will systematically underestimate the population range. Why? Yeah, because a sample can at best have the same range as a population if I happen to pick the smallest and the largest value. But in most cases, it will have a restricted range. Yeah? So it's a range between the smallest and the largest value in a sample will be smaller than the range between the smallest and the largest value in the population. So using the sample mean as an estimate, a sample range as an estimator for the population range is a biased estimator, as it systematically underestimates the true parameter. So here, that is an example from the textbook. Just wanted to clarify a few things because I'm afraid it might be a bit confusing. So here, the figure basically shows two estimators for our population mean. So this is our population mean. This is a population distribution here. It's skewed, as you can see. And so this is the sampling distribution of this or a sample mean, right? So which is one sample mean is one potential estimator of the population mean. And we already learned that this is unbiased, right? So it's on average, so the expected value is the same as the population mean. Another possible estimator for our population mean might be the sample median, rather than the sample mean, sample median. And as you can see, so there are two things that are not very desirable about using the sample median as an estimator for the population mean. The first one is it's biased, right? So for this, in this case here, for skewed population distribution, it systematically underestimates the population mean. And it also has a larger standard error, so it has more variability. So it's less efficient than the sample mean. Yeah, so it's both biased and less efficient, so it's very undesirable. It's not nearly as good as the sample mean. So question for you is what would happen for a symmetric, so if the population distribution would be symmetric? So what would the sample median still be biased? Why yes or why not? Any guesses?
Which was unbiased? Which one?
So if
Just trying to see,
the
because I see like
population, if you had,
slides.
sorry, Kimberly, say it again.
It's okay. No, I just hear your mini me and it's really cute. Which one are you talking about? The larger distribution one or the narrower one? Which one?
No, my question
The
was,
population one or the sample?
so if the population distribution was symmetrical, if let's say the population distribution was normal, so would the sample median still be a biased estimator of the population mean? Yes or no, and why?
Unbiased? I feel like yes, because it's closer to the population mean. And that's just a wild guess. Because
Yeah.
from the looks of it, it is semi close if it was a normal distribution.
Yeah.
But I don't know.
So what is for a normal distribution? What is the relation between the mean and the median?
They're
For a
equivalent.
normal distribution, they're usually all together.
They're always the same, right? So they're the same, at least in the population, right? So that means for a normally distributed population, so the sample median would be an unbiased estimator of the population mean, right? Simply because they are identical. So that is just for a skewed distribution. That is okay. It was just two. Okay. So it's also important to note, actually, the median is an important case because the central limit theorem does not apply to the median. So that means that the sampling distribution of the median is not normally distributed, no matter how large my sample size is, if the distribution is skewed, right? If I don't have a symmetric population distribution. And there is actually, so in statistics, so contrary statistics, we do not have an unbiased estimator for the population median. So there is no such thing. So what we can do is we can use a method called bootstrapping that we will hopefully talk about later today if I have enough time. Probably not, this takes me longer than I think. So to actually correct for the sample median and get a nearly unbiased estimator, which is an interesting exercise. So maybe we can do that in some lab when we're practicing bootstrapping. So I hope that we will get back to that and basically make that link to the estimation of population parameters. Another biased estimator for a population parameter that you might be surprised as a biased estimator is a population variance, is a sample variance. So why is a sample variance a biased estimator? So the reason is that we are using the sample mean. Now we're using a sample mean to calculate the sample variance. And why is that a problem? So when we are so again, we are interested in the true standard deviation of the population, in our population, of the population distribution. And we are using the sample standard deviation as an estimator of this population distribution. And I'm telling you now it's biased. So I'm telling you it's underestimating the true population standard deviation. And I'm also telling you this is because in order to calculate our sample standard deviation, we calculate the average deviation of the scores in our sample from the sample mean. And that is a problem. And the problem is that so the mean of our sample is calculated in a way, necessarily that the individual values have minimal deviation from that mean. And that means that the values in my sample will deviate less from the sample mean than they will from the population mean. Does that make sense? Yes or no?
It makes sense, but I don't understand why.
Okay, so okay, again. So I'm taking a sample from my population, and this sample has a certain mean, right? So I calculate a mean for my sample. This mean will almost definitely not be the population mean. So it will be either larger or smaller than population mean. And now I'm calculating the average deviation of my values in my sample from this mean. That has to be, so this deviation, right? So think about it as if you have the normal distribution, right? And you have the sample mean that is a little bit off the population mean. So it means the values in my sample are necessarily closer to the mean of this sample than they are to the true population mean. There's no way of avoiding that. So it's as long as so only if the sample mean is identical to the population mean, the deviation of my values in my sample from the sample mean will be the same as for the population mean. Otherwise, it will be smaller. Did that help or not at all?
Yeah, I understand it now. Thank you.
All right, super. Yeah, so sample variance underestimates the population variance. And that's why we have to use a corrected formula to obtain an unbiased estimate of the population variance. And that's very similar. At first glance, it might not look any different from the naive formula. So the only difference is we're subtracting a 1 from our sample size. And that will make the estimate a little bit larger, right? Because it's in the denominator. So if he makes the denominator smaller, so we'll make this entire estimate larger, and that corrects for this underestimation. The problem, however, in making this standard deviation or the estimated standard deviation larger, we also make its variance higher, right? As you remember, so the standard deviation of a statistic. So also, right, so that varies with the estimate of statistic itself, and then it depends in some form or the other from on the sample size. So if the statistic itself is larger, then it's standard error. So the standard deviation of its sampling distribution will also be larger. And that makes us less efficient. No? It's less efficient than the biased estimator. So, and that is a situation that we often face in real life statistics. So we have two or more estimators. So, and one might be biased, but it has a smaller, so it's more efficient. So it has a smaller standard deviation. It's less variable. So it's on average closer to the true parameter. And the other one is unbiased, but it's more spread out, right? It has more variability, so it varies more. So the estimate varies more from sample to sample. So then we have to make a decision. So what actually, how do the two values relate to each other? So these two characteristics relate to each other. So does it only have like a tiny bias, but it's super efficient? So then we probably want to work with this estimator. Yeah. So if it has a huge bias and is only a little bit more efficient, then we of course do not want to use it. And for the standard deviation, so we always want to use this one here. Yeah, we always want to use a bias as the unbiased estimator. So very important, right? If you're publishing your results, or if you're calculating the standard error of the mean to plot your data, use the corrected formula for estimating the standard deviation. Okay, so now that we have talked about our point estimates a lot, let's move on to interval estimates, which I already said are the preferred way of estimation for several reasons. I hope that will become clearer as we move on in the lecture. So, and again, so that is just giving an interval on the real number line that we believe the true parameter will fall in. And now a typical, like, my example is always a little lame. So if you want to estimate the mean height of all American males, so we could say, so our estimate of this true population mean is 65 to 71 inches. Yeah, and it's centered at a sample mean of 68 inches. So we could use that range of values instead of the point estimate, right? Instead of the sample mean in this case, so the 68 inches itself. Okay, yeah, and so there's one important thing or two important things to note. So this estimate, so this interval estimate is less precise than a point estimate. Less precise, we're giving a range, yeah, not only one number, we're giving a range of numbers. However, the big advantage is that we can be more confident that our estimate is true. And these two aspects, right? So the precision of an estimate and the confidence that the estimate is true. So these have always a trade-off, right? So you're more confident, your estimate is less precise. Your estimate gets more precise, you're less confident in your prediction. Cannot have both. I mean, theoretically you can, or you'll also talk about that. You just have to increase your sample size. No? Then you can balance the precision and so your confidence against each other. So if you just choose a large enough sample, you can be pretty precise and you can also be pretty confident. Okay, yeah, and we can construct those confidence intervals. So we can construct these intervals that we think the true parameter falls in with a certain prescribed probability. And there's a lot of confusion and misunderstanding. So in terms of what does the probability or the confidence in the confidence interval actually mean? Because there's something like 95% confidence interval and a 99% confidence interval and a 90% confidence interval, right? So what does this 90% actually mean, or the 95%? We will talk about that later because many people misunderstand the true meaning of that. Okay. Anyway, so this probability level is called the confidence level, right? So that's what we call confidence level. So how confident are we? And so, as I said, it's typically close to 1, but theoretically, you can also determine 20% confidence level, yeah, if you wanted to. So it might not make sense, but it is possible. There is no reason why it has to be 95 or 99. So key to constructing a confidence interval is a sampling distribution of the point estimator. If you wanted to construct a confidence interval for our population mean, so then we start with the sampling distribution of our point estimator. So that is a sampling distribution of our sample mean. That is the basis for constructing this confidence interval. And we know, because we know the central limit theorem, so that the Templin distribution for the sample mean and many other sample statistics is approximately normal. Why is that helpful? So we know that 95% of the sample means fall within about 2 standard errors, so from the population mean. Yeah. So okay. That is a little bit here, a little bit confusing. Maybe I will delete that. So if that is our sample mean here, right? So, and this is our sampling distribution of this, so the sample, sorry, it is the population mean. So, and that is the sampling distribution of our sample mean. So then we know that 95% of all sample means will fall in that range, yeah, in the range of so about 2 standard deviations below and above the sample mean, and it is 1.96 to be precise. Okay, yeah, and 2.5% are either larger or smaller, and so we will get to these points here later. And then, of course, we could also say, all right, so that many percent fall within 3 standard deviations from the population mean. So the important point here is that if 95% of all sample means lie within these 2 standard deviations, so 2 standard errors from the 2 population mean, then it also means that in 95% of all cases, the true population parameter lies within 2 standard deviations of our sample estimate. Yeah, and 95%, so if you, again, we take, so we draw samples and we calculate the sample mean for these samples, and we do that repeatedly over and over and over again, then in 95% of the cases, our population parameter, so the population mean, will lie between, so within 2 standard deviations from this sample mean. And so here I have, and that is basically an illustration, right? So let's say, so y bar m is so 1, so the mean for 1 sample. And you can see, right, if we basically, so this is our confidence interval here for this sample mean, and it includes the true population parameter, right? Because the true population, so the true population parameter is within 2 standard deviations, so 2 standard errors from this sample mean. Because the sample mean itself is in that 95% range. Occasionally, we might have a sample where the sample mean deviates more than the 2 standard deviations from the true population mean. And for those cases, of course, 95% confidence intervals that we draw around this sample mean will not cover the true population mean. But for the other, for 90, so basically for 95% of sample means, so for all sample means that fall in this range here, so their confidence interval, right? So this is the sample mean plus minus round, so roughly 2 standard errors, so 2 standard deviations of the sampling distribution will contain the true population mean. Yeah. Okay, and that is the meaning of a confidence interval. Yeah, so if we were to draw infinitely, so an infinite number of random samples of the same size, always important, right? Have to be the same size from the population and construct intervals. Yeah, so around them, so that and these intervals are constructed by just adding so roughly 2 standard errors in each direction. So then the 95% of these intervals would contain the true population parameter. 95% in the long run would contain the true population mean. And this is here all the blue ones. And the red ones, so these are the ones where actually our right? So where our sample mean is actually outside. So it's one of these rare cases where our sample mean is outside the two standard errors of the population mean. So in these cases, the confidence interval would not cover the true population mean. Yeah, but in all other cases, it would. And so this interval, right? So basically taking our sample mean and subtracting, so roughly 2 standard errors and adding roughly 2 standard, so standard errors is called the 95% confidence intervals for mu, so for the true population parameter. So, and it is basically the proportion of such intervals that can be expected to capture, so to contain the true population parameter. So this basically is how wide so the interval is also called the margin of error. Of course, it's always the margin of error is only half, right? Because the confidence interval in this case is symmetrical. So the margin of error is basically the deviation in each direction. It doesn't have to be 1.96, it depends. So it would be different for if I wanted the 99% confidence interval or the 90% confidence interval, right? And I would use the corresponding percentile for of the standard normal distribution. Yeah, so the general formula is our point estimate of the parameter plus minus a margin of error. And that margin of error depends on our confidence level, and it depends on the standard error of the sampling distribution. All right. So, so as I already said, so if we wanted to calculate the 90% or the 99% confidence interval, we would just use a different z-value, right? Rather than the 1.96, which is just the cutoff for this 5% error probability, we would use, for example, 1.645 for a 90% confidence interval, or 2.576 for a 99% confidence interval. So, and then again, right? So there's a systematic relationship between the length of our confidence interval, the confidence level, and the sample size. If we were to increase the confidence level, let's say we wanted to go from 90% to 95%, from 95% to 99%, and we would keep the sample size the same, our resulting confidence interval would be longer. Yeah? So it means our estimate is less precise, but we would be more confident that's accurate. My mouse doesn't work anymore. I don't know why. 1 second. Okay. Did it jump more than one now? Sorry. Okay. If we would increase the sample size n and keeps the confidence level constant, yeah, so then our confidence interval would be shorter. So it means our estimate would be more precise. By increasing our sample size, leaving everything else the same, our estimate would be more precise. So the interval would be narrower. However, so it's not proportional. So in order to get a 2 times more precise estimate, we need to actually quadruple our sample size, right? So if we basically have 4 times the sample size, we have a 2 times more so basically a 2 times more precise estimate of our parameter. It's because we have unfortunately the square root in the n. So it's proportional to the, it scales with the square root of n, not with n itself. Okay, and then so the last thing that we could change is we could change the length of the confidence interval itself. We could say, so how wide do we want it to be in absolute units? So let's say we could say I want the so the mean height of the man in Canada, so by half an inch, right? So I want the confidence interval only half an inch wide. So, and how many men do I need to sample? So how many men do I actually have to observe? So to get that, so narrow of a confidence interval is, let's say, 95% confidence level. So if we kept the sample size the same, so the confidence level would decrease, right? If we otherwise, so we would have to increase the sample size, right? If we wanted to keep the same confidence level. And so that is also one task of your assignment. So that is due in 2 weeks, right? So you have to specify what the sample size is to have like this desired range of your estimate. All right, so let's talk about one example. So we will come back to that example later. Let's assume a flashlight company has invented a new and longer lasting flashlight. And so the company believes that the lifespan of the new flashlight has the same variance as the old model, so it's 16, but they do not know what the mean lifespan is. Right, so they know it's the same, has the same standard deviation, the same variability, but they don't know what's a mean new lifespan is. And to estimate, so the new lifespan, they take a random sample of 100 flashlights and they let them run out. Yeah? And then they basically measure how long it takes. And so the sample mean turns out to be 150 hours. And now, so the task is to find the 95% or the 99% confident interval for the true lifetime of these new flashlights. So what do we know? I already said. So the ingredients that we need is a standard deviation, so the sample, not the samples, the population variation, variance or standard deviation, basically the same, right? Not the same, but we can calculate that. So we know what the sample mean is and we know the sample size. So first of all, we calculate the population standard deviation, right? Just a square root, so that's 4. And then we calculate the standard error of our sampling distribution. And we know that it's just so the standard deviation of the population over the square root of our sample size, which in this case is 0.4. Yeah, that's our standard error for the sampling distribution of the mean. And so now we can determine our so the limits of our confidence interval. So we know that the critical z-value is 1.96 for the 95% confidence interval. So we'll multiply that with our standard error. There, this is 0.784, and then just subtract and add that to our so do not add and subtract that. So we basically do that to our sample mean, right? So and that would result in a lower limit of 149.216 and upper limit of 150.784, right? So that would be our estimate for the true mean lifetime of the new flashlights. And then for the 99% confidence interval, we're doing the same thing. So just the critical z value is different, of course, right? So because we want to be more confident. So and then our interval here, our estimate is less precise, right? So we have a wider interval, but it is also, so we are more confident that actually the true parameter lies within that interval here. So, and as I said, so there are a lot of, it tends to be a lot of confusion so about what the confidence interval actually means. And so often people say that, so a confidence interval has a 95% or 99% probability or chance of containing the true population parameter. And that is not true. So, so a single confidence interval either contains the parameter or does not. So the probability is 1 or 0. For a single confidence interval, there is no 90% probability, it's 1 or 0, right? It's always a long-term probability. So you're always talking about the so a whole set of confidence intervals when it comes to confidence level. Yeah, so and that is, we're also not 95% confident that the true population parameter here is between 149 and 151 hours. So what we can say is that if we were to draw repeatedly, so samples of size 100 from these from this population of new flashlights and would determine so the mean for each individual sample, then so determines the confidence interval around this mean. So the 95% of these confidence intervals would contain the true mean. That's what it means, nothing else. Yeah, that is how we have to interpret the confidence interval. Of course, we are inclined, right? So that is sort of the idea, this intuitive understanding. Of course, we are inclined to believe it is between 149 and 151. But yeah, so we are not 95% confident. And so this is not right. So this one interval is it's 1 or 0, right? Not 95% that it contains a true parameter. Another important thing to always keep in mind is that so all these procedures and these equations rest on the assumption that the sampling distribution is normal. That means so we have to be able to assume that either the population distribution is normal, then it doesn't matter how large our sample is, or our sample has to be large enough that we can rely on the central limit theorem, which tells us if a large enough sample size as a sampling distribution will be normal. And then there's a rule of thumb that says it has to be 30. But so if our population is heavily skewed, and again, I encourage you to use this applet, right, that we looked at earlier. So you will need larger sample sizes. That's just a rule of thumb. You always have to look at your data, right? And so you have to take into account, so maybe you often run simulations to see what it looks like. So you might need considerably larger sample sizes in real life and your real research. So next point, that's all good, right? So nice, we can calculate confidence intervals now. But the problem is that in most cases, we do not know what our population standard deviation is. So the true population standard deviation. Instead, so what we need to do is we need to estimate that from our sample, right? So it's not really it's not because we don't know what the population standard deviation is. And that means if we estimate the standard deviation from our sample, then we also need to estimate, so then we also need to estimate the standard error of our sampling distribution. Yeah, so the original formula, so if you had the true population standard deviation, so then the formula would depend only on the sample size. That means if we know what the population standard deviation is, and our standard error does not change from sample to sample, it always stays constant. However, if we estimate the standard deviation from our sample, then our standard error actually varies from sample to sample. So for each sample, we have a different estimate of our standard error. That means we introduce an extra error in our estimation. And to account for this increased error, we must make the confidence interval a bit wider, right? So there is additional added uncertainty, there's added error. And in order to account for this additional errors, this additional variability, we replace a z-score with a slightly larger score. And this score is known as a t-score. Yeah? That is not the standard normal distribution anymore. That is a t-distribution. And you will hopefully all know, we will go with that in a minute. So a t-distribution very similar to a standard as to a normal distribution. It's just a little bit more spread out. So it has a higher kurtosis. All right. I won't do the confidence interval simulator right now, but so again, I strongly encourage you to check it out. It's also part of your homework. So you have to do it. I'm forcing you to do it to some degree. That's why I will skip it right now. But again, so use that app. So this site with the applets as much as you can. It's so helpful. All right. So the t-score, right? Like a z-score, just from a distribution that's a little bit more, so it has higher kurtosis than the standard normal distribution. And what does kurtosis mean? I know that it should be covered in basic stats lectures, but it's often not. And it's such an important concept. So that's very, very quickly, I will tell you a little bit about kurtosis. Kurtosis tells you something about the tailedness of a distribution. So it basically tells you how fat the tails are. So what do I mean by fat tails? It tells you something about how frequent and how extreme the outliers are in a distribution. And it's typically measured relative to a normal distribution. So often, so many actually standard statistics software packages like SPSS, so they report something that's called excess. And so the excess so that is the kurtosis relative to the normal distribution, the kurtosis for normal distribution at 3. And that's why they say excess is 0. And then basically, so the excess of if it's like larger than, if it's positive, then it's larger than for a normal distribution. If it's negative, then it's smaller than for a normal distribution. So just as a side note. Okay, so we call, if we have a kurtosis, right? So if we have basically fatter tails and a normal distribution, you see that here it's not that easy to see, but you see there are more and more extreme outliers, right? So there is a bigger, so you have more values in the tails here of the distribution. So that is called leptokurtic. If you have a kurtosis that is lower than the normal distribution, then you have less frequent outliers, less frequent extreme values. So you have more modestly sized deviations. You have thinner tails. You see that is here. Often the kurtosis is described as a peakness of a distribution. So how skinny, how narrow, or how wide the peak is. But that's really not that important. It's about the tails. Tails are the important thing about the kurtosis, and why the kurtosis matters so much. And so it is really how much so basically the kurtosis is a measure how these extreme values in the tails of a distribution relate to the variance of this distribution, right? So how they are, so for a given distribution that has the same variance, so how many, so what is the proportion of values in these extreme regions of your potential values? So how many values are actually located farther away from the mean than you would expect based on the variabilities on the standard deviation? So, and why does it matter? Why is it important? So here you have three example distributions that all have the same variance, but they have different kurtoses. So here's a green one has a greater than normal kurtosis. A black one is a normal distribution. You see, right? You see these tails here. So these are fatter tails, the bigger tails of this distribution. And the blue one has a less than normal kurtosis. And you see there's basically the tails are very skinny, right? So very thin tails, there's almost nothing. And so here you have all normal distributions. So they all have the same kurtosis. They just have a different variance. And so only for normally distributed data, only for distribution that has a kurtosis of 360. So all these things that we said about how many values are within, so 1 standard deviation from the mean, 2 standard deviations from the mean, 3 standard deviations from the mean, only for the standard, only for the normal distribution, these proportions are correct. Yeah, only for these distributions here. Actually, yeah, so 68% of all values are within 1 standard deviation of the mean. Not for the green one, not for the blue one here. And so, so it's actually really relevant in real life. So if you can read that on Wikipedia. So apparently, something really serious happened in the financial market in the early 90s, where some hedge fund managers actually ignored the higher kurtosis for some risk variables. So they didn't take into account that certain risk variables had higher kurtosis. And so that means they're underestimated. So there's a chance of higher, more extreme deviations. And so what happened, right? So that was that there was a higher risk, there was higher volatility, and that actually really resulted in the hedge funds to went belly up, and they needed bailing out. So it's something that really happened in real life, where people didn't pay enough attention to this. So maybe not that dramatic difference, but it has a huge impact. Okay, so let's talk about the t-distribution. As I said, it has a higher kurtosis than the normal distribution. So here you see in blue, right, the normal distribution, and you see the t-distribution has these fatter tails here. So it has more, it's a little bit more, we could say it's a little bit more spread out, but that's not absolutely correct. So if we just say spread out, so in most cases we refer to the variance, and that is not the relative measure here. So it really has a higher kurtosis. And another important thing that I want you to remember from your basic stats classes is that the t-distribution, other than the normal distribution, is associated with degrees of freedom. Yeah, so, and that means that its shape, the specific shape of the t-distribution varies as a function of these degrees of freedom. And the degrees of freedom are so basically just your sample size, so n-1 for the t-distribution. So that means for larger samples, so you have a t-distribution that resembles more closely the normal distribution. And for large enough samples, they are actually, so the t-distribution approximates the normal distribution. And so just as a reminder, maybe we will talk about that at some later point again, right? So degrees of freedom in general, so that these are the number of values that are allowed to vary freely when calculating a statistic. And because the standard error for the t-distribution is estimated from the standard deviation, and the standard deviation uses a sample mean, so we are losing 1 degree of freedom. So we're losing 1 degree of freedom because we are so the sample mean is set, right? So we know that so it has to be, for example, 5. And if we would take into account, so if we basically have a sample and we know that sample has to have a mean of 5, and we have 20 values, right? So then 19 of these values could vary freely. But we can choose any number for these 19 values. But then if we have only 1 left, and the sample mean has to be 5, then this one last value has to have a certain, so this has to be a certain number. Otherwise, it wouldn't be 5. And that's why, right? So that's why our degree of freedom gets lost. Just as a reminder, right? So for this concept of degree of freedom, degrees of freedom. Okay. So that means if we have a random sample from a normal distribution, from a normal population distribution, and we don't know the so we don't know what the standard deviation of the population is. So then we can estimate the confidence interval using the t-distribution. So we would just use the critical value from our t-distribution for the 95% confidence interval, 99% confidence interval, et cetera. And so we have to keep in mind, so we have to, that is a different value for different sample sizes. Okay, a few more caveats. So the procedures and equations for these confidence intervals based on t-distributions so rest on the assumption that the population distribution is normal. Yeah, it's no longer the case, as was for the central limit theorem, that so the population distribution can have any shape, right? So if we estimate so the standard deviations from our sample and use the t-values, they're only valid. These estimates are only valid if our population distribution is normal. However, if our sample size is large enough, then the t-distribution looks like a normal distribution. So it means it's robust against violations of the normality assumptions. We don't need to worry about that. The question is always, what is large enough, right? So how large must the sample be? And again, if there are no radical deviations from normalities, and 30 is normally sufficient. However, if our data are extremely skewed or contain extreme outliers, then both methods, no matter whether z-scores or the t-scores, may not be valid. And also, both methods are not valid if our sample was not randomly selected. That is, so always random sample selection is a heart of everything. So all estimation procedures. All right, so always my nice summaries, I don't have enough time, so you can watch that at home. Just want to make a little bit more progress today, sorry about that.
Calculating a confidence interval for...
Okay, it's Dr. Nick again. Love her. She's really good. So, and we have talked about determining the sample size for interval estimates already a little bit. I think it's also not that difficult, and it's part of the assignment. So if you have problems with that or any questions, so feel free to send me an email. I think it's not that hard to grasp, and I would rather like to move on to something that I find more important or would like to cover right now. Okay, let's quickly talk about the confidence interval for proportion. So we already, I mean, you heard that several times from me. So a proportion is nothing but a sample mean. So it's just for categorical data, right? And for categorical data, an observation occurs in one of a set of categories, could be 2, could be 3, could be 4, could be 20. And to summarize the categorical data, we simply record the proportions. So proportions or percentages of observations in the categories. And so what we do is when we calculate statistics for categorical data, we basically focus on what is the probability of a given observation to fall in one category versus all others. So if it falls within one category that we're focusing on, then we basically assign it a value 1. If it falls in one of the other categories, so it will be 1 or 50,000. So I mean, I'm exaggerating, right? So then it is 0. And that is also referred to as success or failure, right? So if an outcome is in the category of interest, and it's also often called as a success, so it's often called a success, otherwise it's called a failure. So there's no valence in it now. So, and if we basically just treat these values like a numerical value, like a 0 and a 1, so then we will see that's a proportion is nothing but a mean. It's a mean for a variable that has only the values 0 and 1. So all the statistics, all the arithmetics, etc., that apply to so a regular numerical variable also apply to the categorical variable if we define the values that way. And so the point estimator for a proportion, population proportion, so the true probability of an observation to be in one given category is estimated by the sample proportion. It's also referred to as p head, and that is a point estimator, the same way that a sample mean is a point estimator. So the head is always, so indicates an estimator, right? So of a true population parameter. So, and that is just a summary of what I said before. So we focus on the probability of an outcome being in a given category, and then it's assigned a value 1, and that is assigned a certain probability. Versus not being in this category, and that is obviously 1 minus the probability of being in this category, and then we are assigning it a value 0. That means our probability mass function would look like that. So like 2 lines, like 2 sticks, also called a stick function. So 1 on the value 0, and 1 on the value 0, 1 on the value 1. So and we can, as I said, we can calculate the mean of this distribution. And so the mean is simply, sorry. So, and this is, I'm just trying to understand what I wanted to say here. Yeah, so that's nothing new. That's basically just what I explained when I was focusing on the graph already, on the figure. Okay. So the standard deviation of this probability can be calculated according to this formula here, where P is the population proportion, right? So it's just the square root of P times 1 minus P. And so the math behind the standard deviation, so the formula for standard deviation is pretty straightforward, right? So we basically just need to substitute. So we can use the formula that we're using for any quantitative variable, and then we are just replacing the y values here with 0 and 1. So these are the possible outcomes. And then we have to multiply it with the probability for 0 and 1, right? And so, and then if we simplify these terms a little bit, we end up with this formula here. So there's no witchcraft to it. It's very straightforward algebra. Not important, just sometimes interesting to see how these things are derived. It's important to note that we can calculate the standard error of the sample proportion very much the same way that we calculated the standard error of the standard mean as a sample mean that we just talked about. So right, it's just the population standard deviation divided by the square root of the sample size, and so we just learned that this is calculated, so the standard deviation can be calculated according to this formula. And it's very important to note that, so this is a population proportion, yeah? So true population proportion. not what we estimate from our sample. And in real life, so the value of the so the true population proportion, of course, is unknown. So we don't know what the probability is of a value to be in a certain category. So and we therefore need to use an estimate of our standard error. And this is also not hard to do. So we just replace the unknown population parameters with the parameters that we estimate, so the proportions that we estimate from our sample. So we just look in our sample and we look how many of our observations are in this category. What is the total number of observations, right? So that's how we come up with the sample proportions, and use that here in this formula. So again, of course, that is an estimate, but it's important to know that as the sample size increases, this estimate gets closer and closer to the true standard error, of our sample proportion. And therefore, for large random samples, and so again, we have a rule of the thumb that we have at least 15 observations in the category, so in the success and the failure categories. For large enough samples, so the estimated standard error gets close to the true standard error. And we also know that the central limit theorem applies. So that means that the sampling distribution of our p hat is approximately normal and centered on the population parameter p, which is nothing but a mean. So you can always interpret the proportion as a mean, right? And read it in this way sense. And therefore, so if we have a large enough sample, we can calculate the confidence interval for population proportion in absolutely the same way we calculate the confidence interval for population mean. And that's another example. Again, I won't talk about that right now. I want to talk about something that is very important. That's not that clear in the textbook. So what are we going to do if we have only a small sample? So we just learned if we have 15 observations in each category, so the success versus failure category, so that means the category of interest versus all other categories, then we can simply use the standard method. We can also, if we have a smaller n, we can use the t method that we just discussed for our numerical values in the sample mean for numerical values. When our sample size are very small, though, then we need to look out for extreme outliers or highly skewed sample data, the same way that I just mentioned that earlier. And so if that's the case, if we have either extreme outliers or we have highly skewed sample data, we need, it makes sense to use a different formula, or a different approach to actually calculate the confidence interval for proportion. And there are three solutions for that. So the first one is the Agresti-Cool interval. Then we have the so-called Wilson score interval, and then it's the Klopper-Pearson interval. So what are these? The Agresti-Cool interval is very simple, super simple, but it's surprisingly effective. So all you do to adjust for the small sample size and potentially so the influence of outliers is you just add 2 successes and 2 failures to your data. That means you simply add 2 observations to each category. So you add 2 ones and 2 zeros. And that in many, many, many cases actually solves the problem. Surprising, but true. So a very easy measure that you can always apply. So another option is to use the Wilson score interval. And that is something that's implemented in R's prop test function. And so the Wilson score interval is a little bit more sophisticated approach, so that deals with the problems that arise from skewed data or very, very small sample sizes. And again, so it is basically estimates the proportion based on this formula, and the NS is just the number of successes, so how many ones you have, so how many values you have in your category of interest, and the NF is the number of failures. Right, so that is just for the sake of completeness, I added this formula, so that is what R's prop test function uses. And then there's a Klopper-Pearson interval. It's also called the exact intervals. It's based on the exact binomial distribution and not the normal, so the large sample normal approximation that we are using when we are using the z-score or the t-score. But that is often too conservative, actually. So that's why it's not typically used. Again, yeah, use our applet demo. Very, very helpful to check out the so the effects of the sample size and the so population distribution on confidence intervals for proportions. Alrighty, so the last 2 minutes I just wanted to use to at least cover so the basics of a very important aspect when it comes to estimation methods. So most of the, or not actually most, but many of the parameters that we're talking about in this class, like the mean and yeah, other estimators, are derived using a method that's called maximum likelihood estimation. And the maximum likely estimation is just so it comes up with an estimate of a parameter that is most consistent with the observed data. So what does it mean, most consistent with the observed data? And it just means that if the parameter, so the true parameter, was equal to that number, the observed data would have a greater chance of occurring than if the parameter had a different number. It just basically determines the parameter in a way that the observed data are most likely. Yeah? So that is basically the criterion for estimating the parameter in a way so that the likelihood to get this particular data in our sample, that this is maximal. Yeah, so that is a way that so these parameters are estimated. And so these maximum likelihood estimators have a bunch of desirable properties. So first, they're efficient, right? So they have smaller standard errors than other estimators. They are also consistent in the sense that if I just choose a sample size large enough, so they will converge to the true parameter. So they have very little bias. And if they have any bias, so this bias will get smaller as the sample size increases. And they have approximately normal sampling distributions. The problem with these maximum likelihood estimators is that we need to make assumptions about the shape of the population distribution. And often, very often, we cannot make those assumptions. And then we have a problem because then can be very, very difficult to find the sampling distribution. So if you don't know what the population distribution looks like, if it's not normal, if it has some other weird shape, so then we often have a problem with coming up with a sampling distribution. And so in this case, we can use a method that is called the bootstrap. And bootstrap is a resampling method. And it just, so when we're doing bootstrap, so we're just pretending or we're treating our sample distribution as if it were a true population distribution. And we approximate the unknown sampling distribution by repeatedly sampling from our sample, right? And calculating the statistics for our newly generated samples. So we basically pretend that our sample is a population and we resample our sample. Okay, sounds a little bit very, very abstract and theoretic, but it's extremely useful. And so we will do that. So hopefully we will get to that a lot and also do that in R quite a lot in this class. So what we are doing, so just in a nutshell, I will be done in a minute. So as I said, so we first draw a sample. And then we have our sample, right? Could be sample for like, I don't know, 50 observations. And then we draw from this sample, another sample with replacement. Yeah? So we do that over and over again, many, many, many times. So and often the sample that we draw from the original sample can be the same size. Yeah, so we have, let's say we have our height, right? So our height data. So let's say we had the height of 50 men from Canada. So, and then we have our sample with a 50 values, and then just sample with replacement from this sample, from these values. So we basically we draw one, we put it back, we draw one, we put it back, we draw one, we put it back, and then we calculate the statistic for each of these newly generated samples. And that way we are simulating a sampling distribution. And that works remarkably well. So that is really here. So I have a video. It's a nice introduction into the idea of bootstrapping. So I highly recommend it to watch that. I ran over a little bit, so I don't want to show it to you right now.
Hi, my name is Brian Caffel, and welcome.
And so there's also a bootstrap simulation in on our applet web page. So we will go over that definitely in our next lab meeting, but I encourage you to take a look at it already. So now to understand what's meant by bootstrapping. So I won't go over the relationship between interval estimation and hypothesis testing today. I will do that next week at the beginning of our class. Just a heads up. So, and I have that here in the slide. So actually I changed that a little bit. So when it comes to interpreting the p level of a given statistical test that we are running, so we have to be super cautious. So how we interpret that and whether we count it as evidence for or against our hypothesis, or as how strong the evidence is. So, and that is referred to in the paper that I posted yesterday. So another reason to read that paper, really important, so it will help you appreciate why it's such a problem to rely only on p levels when we do hypothesis testing. Okay. So that was that for today, and if you have any questions, let me know. Again, I'm sorry that we didn't have time for the videos. Again, I encourage you to watch them while so you're going over the slides. They're a nice summary, and often they use a little bit more visual demonstrations of the topic, right? Okay, so I just try to remember whether there's anything else that we need to talk about. So you have 2 weeks to work on your assignments, and next Monday we will really start working with R. So hopefully you have all read the chapters, so the first 2 chapters of the R cookbook. So otherwise it might be difficult for you to keep up because, as I said, so we will do a lot of sampling, and we will draw samples we'll simulate so drawing samples from various distributions, and we will do a lot of data visualization, so how to draw plots in R using a package, use ggplot2. So yeah. Okay, then have a good night. Sorry for going over, and I'll see you all on Monday, hopefully.
Bye.
Thank you.
Bye.
Thank you. Bye.